Our next speaker is a professor of computer science at Stanford University, where he heads the Applied Cryptography Group and co-directs the Computer Security Lab. His research focuses on applications of cryptography to computer security, and his work includes crypto systems with novel properties, security for mobile devices, web security, and crypto analysis. So please help me in welcoming to the stage Dr. Dan Boneh.
Okay, great. All right, so welcome everyone. It's a pleasure to be here. I'm Dan Boneh. I'm a professor of computer science at Stanford, as was just said. It's really wonderful to see all of you here. I'm really excited to see so much activity around NEO, and I'm amazed at the success of this conference, and I'm really happy to be a speaker at the first developer conference. So thank you for inviting me, and thanks all for coming. Whew, yes. For me, I have to say cryptocurrencies and blockchain technologies are an amazing development, just because it's a wonderful opportunity to deploy advanced crypto systems, and I'm really thrilled to see all this really taking shape and being deployed and used in the real world. What we do is we develop a lot of technology for blockchains and cryptocurrencies that will hopefully take these technologies to the next level. And what I want to do today is tell you briefly about one new tool that we developed called Bulletproofs. And I'll explain what Bulletproofs are for. This is joint work with my students, Benedict Bunz, with Jonathan Boodle, Andrew Palestra, Peter Woolley, and Greg Maxwell from Blockstream and from UCL. We also do a lot of education, obviously, at Stanford. So we do quite a bit of work on telling students and the world about the wonderful things that crypto can do for you. We have courses on cryptocurrencies. In fact, we've been teaching our cryptocurrencies and blockchain course now for 3 years. You guys are welcome to take the class. The class is televised, so anyone in the world can participate and take it even for credit. We have courses on cryptography, advanced cryptography, and we even have a free MOOC that anyone can join up and learn more about cryptography in their own time. So please, make use of these resources. They're there for you and are there to serve you. So as I said, what I want to do today is tell you a little bit about some technology that we developed recently called Bulletproofs. And essentially, this is going to make cryptocurrencies much more friendly towards business. I think Hong Feng mentioned that Bitcoin is used for a replacement for gold, but it's not so much being used for as a currency, for trading. And I want to show you that, in fact, there's a mismatch between the capabilities of Bitcoins and its use for trading. And hopefully, what I'll tell you today will bring it closer to being used as an actual currency, which will greatly increase its use in the real world. So everything that I say will apply to Bitcoin, but I'll use Bitcoin as an example, but everything I say is going to apply equally to NEO as well. So hopefully you can apply these you can deploy these technologies. And I should also say that our code is available. It's all available under MIT license freely. I mean, it's open source. Anyone can use it, and it's ready to be deployed as you see fit. Okay, so what's the problem with Bitcoin? So here's a Bitcoin transaction. If you look at the transaction, you clearly see that, first of all, the addresses of who's making the payments and who's receiving the payments is completely in the clear. Anyone can look at the blockchain and see who's the payer and who's the payee down to their addresses. And it's been shown that it's not that difficult to map addresses into real-world physical identities. So once I know your address, I can pretty much tell that you just made this transaction. And even worse, the amounts that you paid are also public on the blockchain, right? So you can see exactly how much was paid from who and who was the recipient. So the problem is, of course, this is a mismatch for what businesses need. So just think about the business implications of having the payer, the payee, and the amounts all publicly available. The mismatch is, for example, if Stanford wanted to pay my salary in Bitcoins or in NEOs, as I should say here, the problem is that anyone looking at the blockchain could tell exactly what my salary is, right? So that's a pretty big violation of privacy. Moreover, if businesses wanted to use it for their own transactions, say, Ford wants to buy tires from its tire supplier, essentially it would pay the tire supplier in cryptocurrencies. Anyone looking at the blockchain can see exactly how much they're paying for parts, which is basically a non-starter for business. Yeah, so this is just the fact that the amounts are available in the clear means it can never be used to pay salaries. It can never be used for supply chain management and so on. So we have to do something to fix that. And so there's a beautiful idea that I want to tell you about called confidential transactions. Maybe you've even heard of it. It's due to Greg Maxwell from a year and a half ago. And the idea is essentially to hide the amounts on the blockchain. So you will still know who the payer and payee is. So you will know that Stanford paid my salary in Bitcoin, but the idea is you will not know how much they paid. Yeah, and my claim is that is a good level of privacy in the sense that amounts are hidden, but if there's any fraud, you can sort of tell where the money went and maybe try to recover it. But it's crucial that the amounts are not available in the clear to the public. And so what is the idea behind confidential transactions? Where, if you look here, in the current blockchain, the amounts are all available in the clear. With confidential transactions, what we're going to do is we're going to hide the actual amount value, and we're going to replace it by what's called the cryptographic commitment. So, it's a good time early in the morning. I'm a cryptographer. I physically cannot give a talk without doing some math. So I have to put at least one equation on the slides. So bear with me. So what is a cryptographic commitment? A cryptographic commitment is basically a way for you to take a number, like a dollar amount, and put it in an envelope and give it to the world, such that just looking at the envelope does not reveal what the dollar amount is. However, you are bound to the amount. Once you give out the commitment to the world, you can no longer change the value that's inside the commitment. And a very common commitment that's actually used is what's called a Pedersen commitment. So I wrote down the equation for a Pedersen commitment. So if you commit to a value v, what actually gets published on the blockchain is this thing called g to the v times h to the r. Yeah, those are points on an elliptic curve. It's g to the v times h to the r. R is a random value, and that basically hides the value v. So if you look at the commitment, you cannot tell what v is. Yeah, so the amount is completely hidden. So great. So now we have a blockchain where the amounts are hidden. By the way, it's interesting that the fees actually are still in the clear. So a miner can actually look and see how much they're going to be paid and decides which transactions they want to include in the block. But the amounts in the transaction are now completely hidden. But now you scratch your head for a minute and you say, wait a minute, there's a pretty serious problem now. If the amounts are hidden, well, how do we verify the blockchain? Right? How do we know that, in fact, this is a valid transaction? So what does it mean for a transaction to be valid? Well, there's a fundamental equation that every miner has to check. The fundamental equation is that basically, the sum of the input values is equal to the sum of the output values plus the miner's fee. If there's a mismatch, if these two sides are not equal to one another, then the transaction is invalid because it means money is either being destroyed or money is being created. So we have to be able to verify, every miner, and in fact anyone in the world, has to be able to verify that every single transaction on the blockchain satisfies this equality. But now you see there's a fundamental problem that we hit. The amounts are now hidden. You only see commitments to the amounts. You don't see the amounts in the clear. So the question is, how do you verify that the transaction is valid? Kind of almost seems like a contradiction. And actually, this is where the magic of cryptography kicks in. And this is why I love blockchain so much. That finally, these amazing cryptographic tools are being deployed and finding real use. And so the solution is actually to use something called a zero-knowledge proof, which was alluded to in the previous talk. But let me explain to you how that actually works. So essentially, what the person who creates the transaction does is in the transaction, he includes a zero-knowledge proof to say that, in fact, this equation star here actually holds. So without knowing what the values are, you, the world, will convince yourself that, in fact, this equation holds, but you will learn nothing else about the committed values. Well, so I'm kind of ignoring one important fact, which is, in fact, that this is not the only equation that has to be checked. In fact, the other thing that has to be checked is that all the values are non-negative. Yeah, all the values. So it would be terrible if this equation held where the output values were actually negative values. And you should see why, right? If one of the output values was negative, as an attacker, what I would do is I would send 5 bitcoins to one output and negative 2 bitcoins to the other output. That would mean that the total transaction value is 3. 3 inputs were spent, 3 bitcoins were spent, but now I have an output that's worth 5 bitcoins. Yeah? So if I could fool you into accepting transactions where one of the outputs is negative, that would allow me to create coins out of thin air. If I can create coins out of thin air, that essentially translates into inflation. And the interesting thing is, because no one can see the amounts in the clear, No one can tell that this is happening. So if you did not check that the values were all positive, essentially coins would be created out of thin air without anyone ever knowing. The impact of that is essentially hidden inflation, hidden unbounded inflation, because now there are more coins available for the same amount of gold. Yeah, so that's basically what we call inflation. So the question is, how do we have to also prove that all the output values are positive, and in fact they're in a legitimate range. It turns out, oddly, the sum equation is really easy to prove. There's a very easy zero-knowledge proof for the sum. Proving that a value is in a certain range is much, much, much harder. Proving that a value is positive is much, much, much harder. And so the way we do it is using a non-interactive zero-knowledge proof, what's called a NIZK. And in fact, the way, just to give you an idea for how this works, is we have our commitment on the blockchain. The prover, the guy that's creating the transaction, has the value and has the randomizer for the commitment. What he does is he sends a proof that anyone can check. So pi stands for a proof. So anyone can check. They are convinced that in fact the value is in a certain range, but they learn nothing about the value. That's the magic of zero-knowledge proofs on commitments. You're convinced that it's in the right range, but you learn nothing about what the value is. So as I said, this is what's called a range proof. So I give you I commit to a value, and I give you a range proof on that value. And the question is how to do it efficiently. So let me tell you what's known. So before bulletproofs, essentially the best range proofs after very, very heavy optimization. Yeah, this is years of work to optimize this one technique. It's called the Sigma protocol for optimizing these range proofs. It turns out the best you could do is, if the range is 64 bits, the best you could do is you can shrink the proof to 4 kilobytes. So think about that. Every single output in the transaction would have to include a 4 kilobyte proof. Remember the debates about the block size in Bitcoin blocks? That would basically shrink the number of transactions per block by about a factor of 10. Yeah, so that is a real problem. These are large proofs that are a little bit problematic to store on the blockchain. Okay, now even worse, remember, for every transaction output, we have to include a proof. And in fact, if you do 10 proofs, the size now grows by a factor of 10. So 10 proofs would require 40 kilobytes, not just 4 kilobytes. So transactions with large outputs would be dominated by these proof size. Okay, so that's one problem. Yeah, so the proof size is also linear in the range, and there's no need for a trusted setup. So that's the bottom line is a good thing. The size is the problem. Okay, so now let me tell you about bulletproofs. Actually, before I tell you about bulletproofs, you should ask me about another technique called Snarks, or zero-knowledge Snarks, which is a way to do these proofs on commitments with very short proofs. Yeah, so the interesting thing about Snarks is the proofs are very, very short. In fact, they're always 188 bytes, just 188 bytes. So that's a great improvement from 4 kilobytes. So the proofs shrink. The problem is that Snarks actually require a trusted setup. Yeah, today's Snarks require this trusted setup, which means, and they also require this very large public string in the order of gigabytes that's generated in secret, and there's a whole ceremony that goes into generating this public string. You might have heard about that in the press recently. The problem, of course, if the setup is subverted, that means that whoever subverted the setup can now generate fake proofs. They can generate a proof that would convince you, supposedly, that the value is in a given range, but in fact the value will be potentially negative. Right? So if you have this ability to generate these fake proofs, again, you have the inflation problem. And even worse, even if the ceremony was done perfectly and the setup was done perfectly, just the fact that there's a fear of undetectable inflation, which no one will ever know about, because remember, everything is hidden on the blockchain. No one will ever know that this is happening. Just the fear that this is possible is already enough to put a confidential transaction system in jeopardy. Yeah, is that clear? So just the fear of a malicious trusted setup is quite problematic. And so the question is, can we avoid? So Snarks, we want to say are great, but we would like to do things without a trusted setup. And the question is how to do that. So our work on which is called Bulletproofs. As I said, this is publicly available. Anyone can use the code, so please make use of it. What we can do is we have proofs that are much shorter than the Sigma protocols that I talked about before. So notice again here, if you want to do an n-bit range proof, so I want to prove something about committed values. For example, I want to prove that they're in a certain range. Now the size of the proof is logarithmic in the size of the range. Before it was linear, So we reduced it to logarithmic. So you could say it's an exponential improvement in the size, in the length of the proofs. The amazing thing is if you have to do 10 range proofs, the increase now goes, before it was 10 times n. Now the increase just increases additively in log t. So if you need to do 100 range proofs, all you have to do is just add log of 100, which is around 7. You just have to add 7 more elements. You're not multiplying the size of the proof by 100. You're just adding 7 more elements. That's it. So very, very efficient batch aggregatable range proof. And again, the whole point is there's no trusted setup. No need for a trusted setup. So let me show you some numbers, and then I'll stop. So here you have the original proofs that I told you is about 4 kilobytes for proving ranges. Snarks are 188 bytes, but of course require setup. Our proofs are 672 bytes. Yeah, so much, much, much shorter than before. But remember, every transaction has multiple outputs. If you need to do multiple range proofs, before this grows linearly. The size of the proof grows linearly. In our case, the size of the proof grows just by a little bit with more transaction. In particular, if you have to do if you have to do proofs for 10 outputs, the original proof grows dramatically, grows linearly. So it grows dramatically to like 40 kilobytes, which is pretty much unworkable in a block. Whereas our proofs pretty much stay the same size, and again, no trusted setup. Yeah, so that's kind of the point of bulletproofs. I hope this will be useful to you. I guess the last thing I'll say is that they're also very fast for the prover. So when you're building a transaction, you are basically constructing these proofs. And I want to mention that of all the techniques, Snarks, Starks, and the old range proofs, actually even the time to construct the proofs are the shortest with bulletproofs. So they're short and they're very efficient to construct. And so this is kind of a good technique that we expect to be deployed and useful. So let me tell you about some of the applications just so that you appreciate the numbers here. So first of all, as I said, I'm talking about Bitcoin, but everything I say apply to other blockchain-based currencies. So in Bitcoin, the UTXO set is typically, is what miners have to keep in memory. If you use bulletproofs with confidential transactions and a technique called Mimblewimble, it turns out it shrinks the blockchain from 160 gigabytes to only 17 gigabytes. Yeah, so it's an order of magnitude improvement in the size of the blockchain. And again, most of it is because the proofs are so short and are actually aggregatable. The other application I wanted to mention is, it's funny that Faye mentioned security of exchanges and Mt. Gox and the other exchanges that actually lost money. Some work that we did a while ago, back like 2 years ago, basically what it provided was a mechanism in which an exchange could prove in zero knowledge that it's solvent. In other words, the exchange could prove that the amount of assets it has is equal to the amount of obligations that it has. The idea is that every day the exchange would generate a proof like this so that you are guaranteed that the exchange has enough cryptocurrency to actually cover its obligations. If Mt. Gox had done that every day, the problem would have been detected basically 6 months before Mt. Gox went out of business. Yeah, so this is something that I really hope exchanges would deploy at some point. We just need one exchange to do it. Once one exchange deploys a proof of solvency, an automatic proof of solvency, all the other exchanges would be required to do it as well. But we're having trouble finding the one exchange to take the leap and actually deploy this. So if there's anyone in the audience who has influence on any of the exchanges, I think this would be a really good way to increase trust in the exchange system. Yeah, basically, like I said, every day you prove that you have enough assets to cover all your customers' accounts. And it's zero knowledge. So it doesn't leak any information about how much money you have, how many customers you have, how much money they have in their accounts, and so on. So this is a good technique to use. In our original work, we were using the old Sigma protocol method. So the proof every day was 18 gigabytes. It was actually relatively large. With Bulletproof, this shrinks to 60 megabytes. So essentially, anyone who wants to can download this daily proof. 60 megabytes is nothing to download. Just verify locally, and now you have a guarantee that the exchange is still solvent. Okay, so I hope this will get deployed. It's a very practical technique to use, and so again, improved by Bulletproofs. Okay, good. So I think I'll stop here. If you want to learn more about Bulletproofs, I put up the URL here. And as I said, our code is open. We don't file for IP for these things, so please use it. We're just happy when people use our ideas. And yeah, come check out our lab and help help make this a world, a cryptocurrency world. So thank you very much.